Hello. The fundamental theorem of calculus tells us that if we want to find the value of a definite integral, so that's the total change in a function, then we can do that if we can find an antiderivative of the integrand of the function we are integrating. And this theorem then tells us that a good way to approach the problem of evaluating integrals is to understand as clearly as possible anti-differentiation. How do we find antiderivatives? And that is what we're going to talk about in this particular video, and also the next one in the series. Anti-differentiation is really just differentiation going in the opposite direction. So when we have a given function g, and if we can find a function f such that f prime is g, so the derivative of f is g, then we say that f of t is the antiderivative of g of t. And I'll say more later about the use of the word the rather than an antiderivative here, because that's an important point that we'll have to deal with in our development of antidifferentiation. So here are a couple examples. 1/3 x cubed is the antiderivative of x squared, and that's simply because if you take the derivative of 1/3 x cubed, you get x squared. You get 1/3 x, the 3 comes down, 1/3 of 3x to the 3 minus 1, which is x squared. The function tan inverse, or arctan of x, is the antiderivative of 1 over x squared plus 1. And that's because 1 over x squared plus 1 is the derivative of tan inverse of x. And this is a good illustration of why we went through the process of evaluating the derivatives of the inverse tan functions. We need them because they are the antiderivatives of these simple algebraic expressions. Now, there are 3 points I want to make about antidifferentiation. The first is that if we have an antiderivative f of g, so that f prime is g, if we were to add a constant c to f, we would still have a function with its derivative equal to g. Adding a constant to a function does not change its derivative. So, for example, if we took 1/3 x cubed and added 11 to it, the derivative would still be x squared. So whenever you find an antiderivative, you can always add a constant to it and you'll still have an antiderivative. This is actually a very useful fact because when we are using integrals to solve differential equations, we need these constants to adjust our solution to the initial conditions of the model and to further adapt our answer. The second point I want to make is that this adding a constant does not have any effect on the fundamental theorem of calculus. So the definite integral from x equals a to x equals b of x squared dx is just going to be the difference of an antiderivative, 1/3 b cubed minus 1/3 a cubed. So we take the value at the top limit and we subtract the value at the lower limit. And this doesn't change if you add a constant, because if you were to add a constant to the antiderivative, you would be adding it in the first term, but because of the minus, you'd really be subtracting it the second time. So the c's cancel out, the constants cancel out, and so this adding a constant to your antiderivative will not change the value of any definite integral. This is a good point to mention that the dx here in the integral is telling you how you do your derivatives. It's the derivative with respect to x that produces that antiderivative. I've explicitly put here x equals a and x equals b, but most of the time we don't put x equals because the x is always the same over here. x equals a and x equals b is often just written a and b, and we'll see that in our examples as we move along. That's the second point. Now the third point has to do with notation. We write the integral with no limits of f of x dx to stand for any antiderivative of the function f of x. So when we don't have limits, this is actually a function, and really a function class, because it is the most general antiderivative of f of x. So for example, integral without limits 1 over 1 plus x squared dx is tan inverse of x plus a constant. That's simply because the derivative of tan inverse of x plus a constant is what we're integrating here. So without any limits, we actually are using this notation again to represent something different, which is an antiderivative. And we'll see lots of examples here. Suppose your instructor asks you a question like this. We know that suppose that the integral of f of x dx is sine x plus c. So we're just saying the integral of f is a function with its integral equal to f of sine of x plus c. Evaluate the integral from 0 to pi of f of x dx. Well, the fundamental theorem of calculus tells us that we don't need to find out what f is here, because we are told already that we have an antiderivative for it. And so we just evaluate sine at the top limit pi, sine at the lower limit 0, and subtract them, and you'll get 0 minus 0. That'll just be 0. But the point is that a question like this is not asking you to find f of x. You can, because it's the derivative of sine x, so it's really f is really cos x here. But you don't need it that fact to answer the question. Second example, suppose you were to phrase this the other way, so that we're told that the integral of log x dx is some function g of x plus a constant, and then we're asked to evaluate the integral from 1 to e of log of x dx. Well, with this information, what you can write down is g of e minus g of 1 is the value. And here we don't know what the antiderivative is, and we would like to be able to write down what that antiderivative is, and we'll actually need a few techniques before we can actually figure out what that g is. But when we find it, the value of this integral will just be written that way. The last example is a favorite trick question. Instructors of a certain bent love to put this question on tests and exams. The integral from -1 to +1 of the derivative of e to the x squared dx. Now the point here is that the question is asking you to do a definite integral of the derivative of some given function. So we have sitting in front of us the antiderivative. E to the x squared is an antiderivative of its own derivative. And that's what makes this question into such a circular, easy thing to evaluate if you understand the fundamental theorem of calculus. If you integrate a derivative, you really are just going back to that function as the antiderivative. So this question boils down to this: the integral from -1 to +1 of e to the x squared prime, the derivative of e to the x squared dx, is just e to the x squared, evaluated at 1, so it's e to the 1 squared, minus e to the -1 squared. Now -1 squared is +1, so it's e minus e, which is 0. And now that I've shown you this question, you'll never be fooled again.